Hello, everyone. My name is Milan Gupta. I'm from San Diego, California, and my presentation today will be around making a machine learning approach to dysarthria detection, which is a medical disorder. And through this, I'll be analyzing speech impairments, which is the core factor used to detect dysarthria. So I'll set an agenda for my presentation, but first I'm going to go over the problem and kind of explain what dysarthria is and the issue along with it. Second, I'll go over the solution with machine learning and why we use machine learning to do it. Third, I'll go over improving and finalizing the model. And lastly, I'll go over some final thoughts and including my reflection along with a Q&A for anyone who has questions. So, of course, what is dysarthria and what is the problem? Well, dysarthria is a neuromotor speech disorder that makes it difficult to speak due to problems with the muscles used in your mouth that allow you to speak. So these muscles are typically used within your voice box, and this can cause a wide array of signs and symptoms. So you can see words being slurred, you can see rapid speech, you can also see strained or raspy voice sounding voices. And as you can see in this chart here, there's a lot of different symptoms, which is something you need to keep in mind when making a machine learning model because it's not exactly one symptom means you have this or not. There's a wide variety and vast amount of different things that can indicate dysarthria. So the neurological impact of dysarthria is that it often points to neurological disorders including Parkinson's, MS, and ALS. And the reason this is important is because these disorders often can lead to neurological issues, and those neurological issues can often impact your voice box, which can cause dysarthria. So that's why we use dysarthria, or many professionals use dysarthria as an indicator for your brain health. And it can also be used to indicate stroke, a traumatic brain injury, or even brain tumors. So who does it affect? Well, 30% of people with ALS have conditions and symptoms of dysarthria. People who have MS are often 25 to 50% of the time affected. People with Parkinson's, 70 to 100% of the time they are affected. People with stroke, it can vary a lot, but you would see it around 8 to 60%. And people with a traumatic brain injury, you will see it around 10 to 65%. And the reason these are varying percentages and are not just one is because the level of dysarthria is different for everyone. You can have a lot of slurred speech, you can't say anything straight, or you can say something straight, but you can't say it all. And I think this is really important because machine learning is able to distinguish these issues and make patterns that allow us to detect dysarthria. And of course, why do we even use machine learning? Why can't we just use our ears and determine if this person has dysarthria or not? Well, like I said earlier, it's the variation with this problem. So we don't really know what the issue is completely. We may know some symptoms, but what if they have multiple symptoms? What if they don't have any symptoms, but they still have it? The point is that machine learning offers a promising avenue to address these challenges because it allows for more precise and scalable tools. And when I mean scalable, I mean that machine learning can build off of previous data. So when you have a data set, machine learning learns off of that data set. But then when you have more patients and more people who have dysarthria or don't have dysarthria, the machine learning model can take that data, implement it into its model, and it can improve off itself and be more accurate. So how are we implementing machine learning and how is it used here? Well, first, you have to make the model. And to make a model, you need to get data to train it. So the database I used was from a site called Torgo, called Acoustic and Articulatory Speech from Speakers with Dysarthria. And the schema of this database was that there were 4 sections, and those 4 sections were comprised of a male and female control group who did not have dysarthria, but it also consisted of a male and female group that had dysarthria. And there were around 500 files each for people with and without dysarthria. And as you can see here, this is kind of the naming convention that was used in the database. And for here, we would signify this as someone who has dysarthria because it does not say ND. So ND would mean non-dysarthric. But how do we can't just use the audio and we can't determine if they have dysarthria. We have to take features from the speech itself. And we use MFCCs, which are male frequency substitute coefficients. And we take that from the speech that we get in the data. Now, these coefficients represent the phonetic characteristics of speech for each audio file. And if you look over here on the right-hand side, that's a pretty big equation, and I guess it'd be confusing for many people, but there's a reason we're not going too into that, because there are tools that allow us to take the features out and utilize them so we can make the coefficients, as you can see here. So once we do that, we have to format the data, because we can't just input the data without telling the model, okay, what does this data mean? Is this data mapped to someone who's dysarthric, or is it mapped to someone who isn't dysarthric? So that's what we do. We take the x value, like in a linear equation, and we use that as the input, the independent variable. So what I mean by that is we use these coefficients here as our input, and we map that to a y value, because we know if this person is dysarthric or not dysarthric. That is how we format the data, because we need to train the model. We need to give it parameters that tell it what to do and make patterns based off of the data it's given. So how do we make the model? Well, we have to initiate it, and in most cases, when you're using MFCCs, or the coefficients I was speaking about, a CNN or a convolutional neural network will be your best bet. And this is because it's best fitted for these coefficients. So here's a bit of a line of how we make the model. So like I said, we get the data, we have to clean and manipulate it. And that's what the MFCCs did. And I'll go into these steps here just in a moment. So I'll go over what a CNN is, because it can be pretty confusing once you hear it for the first time. So think of a CNN as part of your brain, and you can think of these layers here as emulating your brain, except on a very big level and powerful level, because we're using the power of computers. And essentially, the formal definition of a CNN is that it's a deep learning algorithm that can take an input, assign importance to various aspects in the input, and differentiate one characteristic from the other through a series of layers. And these layers, as you can see here, we call them dense, pooling, and a convolutional layer. And here is what I use for my final model. And as you can see, I won't get too into it, but if you could think of it, having more layers allows the model to find more characteristics of someone who is dysarthric, or find more patterns of someone who is dysarthric. So if we had one layer, it wouldn't be a good idea, but since we have multiple and a lot of different shapes, that allows the model to find good patterns and determine if someone is dysarthric or not with a high accuracy. So once we have an idea of what we're going to do for the model, we have to improve it, we have to make it more accurate, and that is what this section is about. So there are different ways to improve your model, but the one I did was I changed the layers. So as you can see on the right-hand side, if you look within the model frame right here, these two sections of code aren't similar. They're pretty different, and they have different characteristics, and that's what makes machine learning and training your model so important, is you have to experiment, try new things, and adjust your parameters to get the best performance and accuracy. And when I was doing my research and making my model, I had to make over 20 different total models, and that kind of shows the importance of staying consistent and persevering, because it's not an easy task to make one model. It takes a bit of time, because there are a lot of errors that can come along with it, and your code won't run. So that's an important aspect that you have to take into when you're doing something with machine learning. So now I had to test and validate the data. And here's how I did this. So I have my database, but when I have my database, I'll split 80% of it to train the model, and I'll split 20% of that database to test it. And the reason I split it up is because we want the model, when we're testing it, to see unforeseen data. We don't want them to know what this data is, and if it's been being used within the model to train it, of course it's going to accurately determine if it's dysarthric or not dysarthric. So that's why we validate with new data that the model has not seen, because it will assess and use, it'll emulate real world applicability and performance. So with my final model, I reached 95% accuracy, or approximately, and this is pretty accurate considering previous models for Dysarthria, which were around 93%. But the importance of this 2% is that it's a lot harder to go from 93 to 95% than it is to go from 79 to 81%, because you have to be very, very accurate. Now, here is what we call a confusion matrix. And to break it down for you, if you look here, we have around 998 files, 991 files, and this is for dysarthric and non-dysarthric speech. So out of the 998 files that were dysarthric, we correctly identified 950, but we miscorrectly identified 48. And as you can see here, for those who are non-dysarthric, we correctly identified 939 and incorrectly identified 52. And that gives us our final accuracy of 94.97, which you saw in the last slide. So here are some previous accuracies from my other three models. And as you can see, I progressed very well, and that was an important step for me because I had to keep persevering and get through each model and improve from the last one. So I went from 83 to 92 to around 92.5 to 95. And there were a lot of different models along the way, but one thing I noticed was that when I got to 92, my next model dropped to 87, and I had to continue to tweak it. And I had to go back to this model and then make some new changes so I could reach 92.5. So here are my final thoughts. I think formatting data is one of the most important things that you could do in machine learning because it can take time to improve and validate your model. And if your data isn't good, your machine learning model is nearly worthless because it doesn't know what to map an input to an output. And secondly, making an accurate machine learning model takes a lot of time, and it's really important that you continue to learn new methods and strategies along the way because that is how you grow as a researcher, as a person, and that's how you grow your character because it takes perseverance to make something good in the end. And without further ado, if you guys have any questions, please let me know. I'd be happy to answer them.
Thank you. Thank you for the presentation. You mentioned perseverance a few times. Can you talk about why that was important to you or what you learned from that?
Yeah, so this project took me and my mentor, I guess, 6 to 7 months. Um, and the reason I say perseverance is because in the world of machine learning, there's a lot you don't know, and nobody knows everything. So that's something that you have to take into account when you're doing a research project. And I think making the models and going down in accuracy from before and having to go back up, that takes perseverance because you can be discouraged very easily. You're like, oh, I'm fine with this accuracy. If I'm already going down from here, then why should I continue? But that's a core, I think, thing I took away from this was persevering, and then you can always get more. I still think I could probably get more. It'd just be very, very hard and probably not worth an extra few months, but that's yeah, something really interesting I took away.
I mean, the whole presentation was fascinating, but I really loved the story of progression, right? And you could have easily stopped at 92.5, right? But it was like, no, you kept going and you got to 95% accuracy. So did you just use you tested the data off of those files with the men and women?
Yeah, that's
Yeah,
correct.
that's great. Any other questions from the group? I think it's a good lesson in perseverance and a really cool idea and cool topic idea. Thank you, Milan.